Hello, this is part 4 on the section for nonlinear data regression. We've seen power functions in an example. We've talked a little bit about exponential functions, and now we want to do an example for that. And so here we have population data for the United States from 1790 to 1850, and we would like to fit an exponential function to that data. A couple of different ways. Notice in chapter 3 we give you the technological background to do it on a spreadsheet or using semi-log paper. And we'll do the semi-log paper first and then look at a spreadsheet. So one thing to be aware of is if you're using a spreadsheet, then the more likely form you're going to see is something like this form, y equals a times e to the kx. And if we're using semi-log paper, it makes more sense to use something of the form y equals a times 10 to the bx. And we can, of course, go back and forth between the two, but just be aware there is a difference. And the reason for that is with semi-log paper, it makes sense to do things in base 10. So if I do the common log of y equals the common log of the right side, then the right side becomes the log of a plus bx, because just like before, log of 10 is 1, and so we're just left with bx. So what I need to do then is I need to plot the log of y versus our regular x values. So this, of course, is our x values. This is our y values. So we need to transform these y values. But we also need to transform the x values, and that's where the hint comes into play. It says shift the data horizontally. And as we mentioned in our last video, in either case, if I put numbers that are close to 2,000 in this exponent, to make this model work, we're going to have to get a really small number for the coefficient, and or possibly this coefficient. So one way or the other, it's probably going to be an unwieldy model, and we can save ourselves some trouble by transforming it. And so the transformed x would be, just let 1790 be year 0, and then we have year 10, 20, 30, 40, 50, and 60. Okay, and whether you do it by hand or on a spreadsheet, that's not bad. And there's nothing special about the x value, whether you call it 0 or 1790, as long as we are consistent in what we're doing. So what does this look like on semi-log paper? So as expected, the horizontal axis is just a traditional graph paper because we're not transforming the x other than the shift, which we can indicate here with a 0. And because we're going up to 60, we'll go by 10. So 10, 20, 30, 40, 50, 60. It's not ideal. We might want to spread this out more so we get a little less kind of error if we wiggle our line a little bit. But for this data, I think we'll be okay. And then recall our y-axis is logarithmic because we are transforming that data. Notice we're going anywhere from 3 to 23, so we don't need very many cycles. So we will just leave this at 1 and leave this at 10, and then we'll have 100 up here. And that should be enough for all of our data. So notice in this case, we do have a 0 axis, so when we're interested in this intercept, this will be the intercept we need, so hopefully the line will pass through that vertical axis. Otherwise, we'll have to do something similar to the previous example. So there's our data. Again, I encourage you to plot this on your own first, and then you can check your answer with mine. And here's how I would do it. So 1790 is 3.9, so that would be about there. 1800 would be 5.3, about there. 1810 is 7.2, so about there. 1820 is 9.6. 1830 is not quite 13, which I've got, that's 15, 12 and a half, so maybe about there. 1840 corresponds to 17.1. This is 17.5, so a little below it. And then 1850 corresponds to 23. There's 20, 20, so yeah, somewhere a little below that line maybe. So, good news, we get a plot that looks very linear, so that means exponential was a good choice. This transformation has done its job, and so we can plot the best fit line. In fact, if I want to, I can extend this further. All right. Okay. So now we're trying to find our slope of the line and our coefficient. Now the coefficient is not bad. It's just going to be, since we have the zero intercept here, we can just read it directly off the graph, and that's 4. So 4 is equal to A. Now, you might be thinking about our transformation as the log of A, but notice these are the logarithms of A, so the value is just directly read off of the graph. So I have my coefficient overall completed, and so now we just need the slope. We can't use the method we used in the last video because we don't have logarithmic cycles on both sides. In fact, my advice is to think about it in terms of rise over run and do it in a special way. And here's what I mean, is let's find one cycle of data, okay? So, and that's going to give us a rise of basically 1 order of magnitude. So for example, if I look at here at 100, it looks like it crosses about here, okay? And if I look at 10, it looks like it crosses about here. So that looks to me like maybe 32. And this looks to me like we need more numbers. 70, 80, 90, 100, 110. So maybe 112. So if I do the rise over run, this gap then is 80 years. And then this rise is basically the log of 100 minus the log of 10 because it's transformed. So the log of 2 minus, so that would be 2 minus 1, which is 1. In fact, one cycle will always be 1. So generally speaking, if you can find 2 points that the line passes through, then that cycle will give you a rise of 1. And as long as your line isn't super shallow, that shouldn't be too bad. So that gives us our slope. So our slope then is just the rise or run, so 1/80th. So that gives us a model of y equals 4 times 10 to the 1/80th x. Or if you prefer, 4 times 10 to the x over 80. Now, if we wanted to go back and compare that to our original function, we could set e to the k equals 10 to the b, right? Or in other words, e to the k equals 10 to the 1/80th, because everything else is the same. And then if I take the natural log of both sides, then notice natural log of e reduces to 1, so I have k equals the natural log of 10 to the 1 over 80. And then if we're curious what that is, we can calculate the natural log of 10 to the 1 divided by 80. And so we get about 0.288. Again, there's no point in taking too many decimal places because this method isn't precise enough to get much more accurate than that anyway. Okay, so we're getting an intercept of 4, which makes sense because our population in year 0 was about 4. So that's not a surprise, 4 million. And the coefficient of the exponent is really what we're going to need the effort to work on. So before we try this on a spreadsheet, notice we can answer some of the questions for using the log paper. First of all, is it a good fit? I would say yes. Exponential does a great fit for the US for those 60 years. If we wanted to look for 1870, 1870 would be 80 years later. So 80 years would be somewhere around here. So it looks like that's about 40 million. 1900 would be 110 years. So 110 is up here. At, what is that, maybe 95 million. 1950 would be 50 more years after that. So 10, 20, 30, 40, 50. So 1950 would be up here at 400 million. And 2000 would be 50 more years, 10, 20, 30, 40, 50. So that would be right up here, which would be, we need another cycle. And so if we come over, that would be about right here. So remember, this represents 1,000, this represents 2,000. So this would represent about 1,500. So that's, we'll call it 1,600. So in other words, this represents about 1.6 billion people in the United States, which, as you may know, is nowhere near accurate. So long-term extrapolation, even this number in 1950 is clearly wrong. If you're not sure about the population for these numbers, we will look those up here in a moment. But as far as for interpolation and for fitting the data we have, it looks like the exponential function and the semi-log paper did just fine. So now let's take a look at a spreadsheet. So here's our data once again, and we can just try to find a exponential trend line. So we hit exponential. Notice it does fit the curve, it looks good. But when we try to find a formula for that trend line, notice the coefficient up here is fine. And in fact, it's even pretty close to what we had on the semi-log paper. Notice it's about 0.029, like what we found before. But this coefficient here is 4 times 10 to the negative 23rd power. And that's not easy to work with. And it's also, with only one significant figure, probably is not going to be very useful for modeling. So this is not the best way of trying to tackle this. So let's shift the data. So since 1790, it's going to be this minus 1790. And then I can just copy and paste this over. All right, and then we can insert another scatter plot. Of course, it's not going to look any different, except for the x-axis. But now notice when I add a trend line, my r squared doesn't change. I get 0.9999 either way. But now notice I get a formula that's a lot easier to work with. And so if I did want to try to use that for prediction purposes, I could. So I could say 3.937 times the exponential of 0.0295 times years in 1790. And then I can drag this down to 2000. And we also need to drag this down. And drag this down. All right. So we have more decimal places than we really need here, so we will try to clean this up to be consistent with the data we're given. So notice it looks great here for the first so many years. Visually it looks good, numerically it looks good. 23.1 versus 23.2 million in 1850. We mentioned about predicting for 1870. Our semi-log model got 40 million, Excel gets 42 million, and the actual is 39 million. So not too bad. For 1900, our semi-log model got 95 million, Excel's getting 101, and now we see we're starting to get some error, 76 million. So we're quite a bit off there. And then of course by 1950, we're nowhere close, over 440 million versus 150 million. And of course, the year 2000 is even worse. So it's a lesson in the dangers of extrapolating exponential function. Things can be exponential for a while, but often they don't continue to be exponential, or maybe they never were exponential. Maybe it was just a good fit for a short window. It's hard to say. Obviously, historically, America had a different history for those first so many years where maybe exponential growth might have been more realistic than in more recent years. But for our purposes, we're just trying to understand how to find the best possible exponential. And because this is such a great fit, we don't have to worry about any funny business with the transformed SSE being different than the regular SSE. So we can be satisfied with this model. So that's it for this part. We will move on to polynomials in the next video.